All right, today we're going to talk about domain and range. Mostly we're going to talk about domain. Range also a little bit, but really this is more about domain. I feel like you can't see that very well. Can you see that all right? Is it visible? I feel like I can't see it very well, but maybe I should do this stuff a little better. Why does that look funky? I don't love that. Okay, there we go. All right, cool. So domain and range. I know I've alluded to domain and range many times. When you think about domain, you're really just thinking about all the things X is allowed to be in the function. So if you're writing your function as a function of X, which we typically do, it's all of the allowed input values, which is what we've written here. All possible values of X can be plugged into a function. We can find the domain. Sometimes we're looking at the graph, although it's usually not the fastest way to find the domain. We can also do it algebraically, which is more typical. And then the thing I would say is lots of functions, most functions we encounter typically are going to have a domain of everything. There's only really a select few types of functions that have a limited domain. Now we're going to see a lot of them because that's kind of the point, but most things you encounter, their domain is everything. And one prime example of this is something like f of x equal to, 2x to the fourth plus 7x squared plus 3. That function, a polynomial, has a domain that's everything. So it has domain all real numbers, which you can write either as fancy R, I like the fancy R, or as everything from negative infinity to infinity. And what I wanted to point out is generally all polynomials have a domain that's everything. So, and so do all polynomials. So with one kind of exception we'll learn about later on, there's really only 3 types of functions that have domain restrictions. When you have things that you can't do. And one of them is division by 0. So if you have some sort of division by 0 in your function, it means you probably have a restricted domain. So what do we do? Well, for example, if your function was, I don't know, 3 over x minus 2, 2 wouldn't be in the domain because if x was 2, you'd be divided by 0. But the way we typically deal with this is we set the denominator equal to 0 and exclude all solutions. Can't divide by 0. Okay. There's 2 other things that are problematic. One's taking the square root of a negative number. So actually, we should be more general, not just a square root, any sort of even root. So a 4th root, a 6th root, an 8th root, a 1000th root, any even root, we can't take an even root of a negative number and get a real result. Right there, you can totally take the square root of -9 and get an imaginary number, which we're not dealing with in this class, but which you will definitely deal with if you're taking the 7 series specifically. Like all the series kind of go, the 17 series really, like imaginary numbers play a big role in 17B, bless you. So just be aware they are possibly in your future. But for now, we only want real results. So if you have an even root of a negative number, that's a problem. That gives you not real answers. So the way we deal with that, or the way we find the domain for a function like that, is we take whatever's inside an even root and we say, well, it has to be non-negative. So we're going to set whatever is inside the even root to be greater than or equal to 0. An example would be something like the 4th root of x squared minus 9. There's lots of examples. I should also mention, just since we're talking about roots, odd roots are totally fine. You can take a key root of a negative number, a 5th root of a negative number, any odd root of any negative number is totally going to give you a real answer. It might not be a nice answer, just like the square root of 5 is not a nice, easy integer number. The cube root of -7 is not a nice number, but it's still a real number. There is an actual number that if you cube it multiply by itself 3 times, it equals -7. It's something like -1 point something. It's right. It's almost -2, but I don't know what it is. And then finally, the last issue we run into is, sorry, I don't write this yet. Taking the logarithm of a negative number. Actually, I should say of 0 or a negative number. That is the last issue we run into. So for example, you might say something like f of x equal to log base 2 of x minus 3. And we've kind of already seen this specifically, like when we talked about solving logarithmic equations and we had to check for extraneous solutions. That's because those extraneous solutions worked in the domain of the logarithmic expression. So we're just kind of expanding on that. You say, okay, we want to find the domain of a function here. We have to make sure we don't take the log of a negative. So the way we deal with this is set whatever's inside the logarithm, set the insides to be strictly greater than 0. Okay, so those are the 3 main things you'll run into when you're talking about domain. If someone says find the domain of a function, look for division by 0, look for an even root, look for a logarithm, and if you don't see any of those 3 things, typically the domain is going to be just all real numbers. I will again say there is one exception to that statement when we talk about inverse trig functions later on, but aside from that, really that's it. So there's only real 3 big picture kind of, is it this, this, or this? Okay, great, then we're done. The range, on the other hand, well, just like the domain is all possible x values, the range is all possible y values. And for now, we're just going to talk about the range as doing it graphically, looking at the picture and seeing what the y values are. Next class, we'll talk about how to find the range using inverse functions, like a kind of a class. So for now, that's fine. Next class, we will cover how to find the range algebraically. Okay. So we're just gonna do some examples, right? We've talked about the thing. There's 3 things you can do, and now let's example it up. Like anything else I really want to say here? No, not really. Sure. So actually, before you turn to that, sorry, I know you all just turned to the next page. Before you turn to the next page, let me give you a couple examples of functions that have a domain that's everything. So for example, f of x equal to the 7th root of x minus 3. There's no issues. There's no division by 0. There's no even root of a negative number, and there's no logarithm. So this function, keep doing this thing right, has domain all real numbers. In a similar way, so does this function. 2x plus 9 over x squared plus 7. Whoops, you can't see that very well, sorry. Even though this one looks like you could possibly have division by 0 because there is a fraction, that denominator is never going to equal 0 because it's always greater than or equal to 7. Come on. So this one also has domain everything. There's no logarithms, there's no even roots, and the denominator never will equal 0. So just a couple examples of things that are defined there. And of course, something like h of x equal to 3 to the x minus 1. If I was asking about domain, I would look for the 3 things. I don't see any fractions. I don't see any even roots. I don't see any logarithms. So there's no domain issues. So this thing also has domain everything. And yeah, you can write it like this, or you can write the fancy. I like the fancy R. All real numbers. Okay, well, let's now you can turn it in. So some more examples. We got more examples. We'll also talk about the range of these because we're going to look at them graphically. So that's kind of the point, is you can certainly find the range of a function if you can graph it. So let's look at something like f of x equal to x squared minus 2x minus 15. And before I do anything, I'm going to say, well, I'm talking about domain. There's no roots. There's no division by 0. And there's definitely no logarithms. So the domain is everything. Everything from negative infinity to infinity. On the other hand, this is a parabola opening upwards. And I don't really want to do all of the details of graphing it, right? This problem didn't say graph it, it just said find the domain range. We're going to graph to find the domain range. But really, when you're finding the range of a parabola, all you really need to know is 2 things: which way it opens and where the vertex is. Because that's all you need to know to find the range. Yeah, I know we could do a better job graphing it. I'm not going to do a better job graphing it. I'm just going to use what I have to find the range. So let's find the vertex. The x coordinate of my vertex is negative b over 2a, which is negative negative 2 over 2 times 1, which is 2 over 2, which is 1. The y coordinate of the vertex is, let's see, plug in 1. F of 1 is 1 squared minus 2 times 1 minus 15, which is 1 minus 2, which is negative 1, minus 15, which is negative 16. So way down here at negative 16, right? My graph's not even here. Clearly, I wasn't planning on graphing this. But way down here at 1 negative 16, that's the bottom of my parabola, and then it just opens upwards. And my graph is not going to be very good. I'm sure these are not my actual x-intercepts. That's okay. I don't care. What I do care about is thinking about what all the y values are. So if I think about the y values here, I can see, well, my y values go as low as negative 16 and as high as forever. So it looks like my range is a bottom of negative 16 inclusive, right? We do definitely get a y value of negative 16 up to infinity, forever and ever and ever. So you can definitely find the range of a function graphically. Again, some functions are easier than others, depending on the graph. Some of the polynomials we've graphed in a couple classes ago, it would be hard to find the range because you might not be able to find the top or the bottom of them necessarily, but it's generally a good approach to at least think about. All right. If you got questions, ask them. If it was a downward opening parabola instead, the range would go from negative infinity up to whatever the y value of the vertex was. And parabolas will always have limited ranges. You never get everything with a parabola or an even degree polynomial in general. All right, let's do this next one. Domain and range of natural log of x plus 1 plus 2. Okay, so now we have one of the 3 things. We have a logarithm. So if there's a logarithm, we need to set the insides of the logarithm, x plus 1, to be strictly greater than 0. Which means x is going to be strictly greater than negative 1. And it might help, although you certainly don't have to, you could draw a number line to help you write the answer in interval notation. There's my negative 1 right there. I want everything to the bigger side of negative 1. So I want everything from negative 1 up to infinity. So that's my domain, negative 1 to infinity. We can graph it. I guess we might as well graph it. So I've shifted it left by 1. So my vertical asymptote is now at x equal to negative 1. And down by 2. I don't really care about shifting it down by 2. That's fine. So it'll look something like this. I guess I could find the y-intercept. So I plug in 0 for x. Natural log of 1 is 0. 0 plus 2 is 2. There's my y-intercept. There's my not very good graph. It's okay. Doesn't have to be perfect. Does the logarithm ever stop going up? No, right? There's no horizontal asymptote for a logarithm. It never like levels out or turns around. It keeps going up and up and up. Now, if you graph it like on a nice graphing calculator or Desmos, you will see that it gets very, very gradual, right? You're going up, 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 but like not very fast at all. But it still does keep going up because every time you plug in a bigger x value here, you're going to get a bigger y value out. So the range for a logarithm is always going to be everything. Unless you've cut it off in some way, like with a piecewise function. But if you just have a regular logarithm, shifted up, down, left, right, reflected, whatever, it's always going to have everything in the range. Yeah.
The last one, Why did you use a bracket?
Good question. Why did I use a bracket? So we use a bracket to indicate that we want to include that value. So definitely this function does actually have a y value that equals -16 when x is equal to 1. On the other hand, this one over here, I did not want to include the -1. Right? We can't plug in -1 here because you plug in -1, -1 plus 1 is 0, and we can't take a logarithm of 0. So we're using a bracket when we want to make sure that value gets included, and in parentheses when we want to make sure that value is excluded. But you want everything next to it. So like, I don't want -1, but I want -0.999999999. So yeah, and then I should just say also, infinity, we always use a parentheses for, because we can never actually include infinity because it's not a real value, it's just a direction. So infinity always gets a parentheses. Never a bracket. Good, thanks for asking that. I should have said that, but I'm glad you asked. Okay, let's look at kind of an inverse function of this, although not exactly, but close to it. Something like e to the x. Just like I mentioned last time, inverse functions, x and y things kind of switch. So here's our exponential function. Looks like this, kind of. And the domain is, well, there's no issues, right? Domain, no issues to be seen. So we get everything. Domain, negative infinity. The range, on the other hand, we certainly don't get everything, right? We do not get every y value. Do we get any negative y values? No. Do we get 0? No, we get really close to 0, but we don't. So you can get any value that's positive, right? Because you can keep going way out to the left here and get closer and closer to 0, but you never actually get there. So our range here, well, y has to be strictly greater than 0. So our range is going to be all positive numbers. So our range is going to look like everything from 0 exclusive, because we don't want to include 0, because 0 is not a positive number, to infinity. Just in case I haven't said this before, or no one has said this before, 0 is the only number that's neither positive nor negative. 0 has neither sign. Every other real number we encounter is either positive or negative, but 0 is the only one that's not. So we're just looking at the graphs. Let's look at the next one. The main range of the square root of x. Okay, so now again, we're seeing one of the 3 main things we look for when we're talking about domain. Is there a division by 0? No, but is there a square root or an even root? Yes, there is. So when I look at this domain, I'm seeing my function is the square root of some stuff. And I know that that stuff has to be non-negative, greater than or equal to 0. 0 is fine for a square root. It's not fine for a logarithm. Okay, so we need to say that our x plus 9 needs to be greater than or equal to 0, which means x is going to be greater than or equal to -9. This is also how I graph this function, by the way. Like, I know we've talked about shifting, and you can think about how this shifts. Like, if you look at this, you're like, okay, there's a 9, I'm adding 9 and then it's going to shift 9 to the left. Honestly, when I'm thinking about this, I'm thinking about what the domain is, and then being like, oh, the domain is starting at -9, which is 9 to the left of where I usually would have started, and that's how I really kind of actually think about graphing. Maggie, do you have a question, or you just? Okay, cool. All right, so 9 to the left. My square root function starts over here at -9, and then it goes up and up and up and up like that. My domain is looking like. Do I want to include -9 or not include -9? I want to include, because x can totally be -9, because -9 plus 9 is 0, and the square root of 0 is 0. Lots of people, the reason I point that is because lots of people, in my experience, I've seen lots of students over the years leave the square root of 0 as the square root of 0 and not to simplify it as 0. You should always simplify the square root of 0 equal to 0 and the square root of 1 equal to 1. because they both simplify very, very straightforwardly. So domain, I'm writing the wrong thing here, that's fine. Domain, I should write down here. It's going to be, I should write, well, yeah. I should just do the thing. -9 to infinity. Typically, when people ask you to write domain or range, the preference is interval notation. So even though you might want to be like, well, domain is x greater than or equal to -9, it's more correct to write it this way. So I would encourage, request that all of you do try to do it this way, because that is what is generally preferred. There's also this thing called set builder notation that some people like to do, where they say the domain is the set of all x's such that x is greater than or equal to -9. That just feels like a giant pain to write out when you could just write this smaller notation. So again, I would say you should do it this way. Range. We're just looking at the graph. So even though I didn't, at that point there is a -9, 0. And so it looks like my lowest y value is 0, and they just go up and up and up and up and up. So my range is the y values are greater than or equal to 0, which means we're starting 0 inclusive and going up to infinity. Yeah. Yes, exactly. So for when you have the case where you have everything, you can do the fancy R. Yeah. But if you have anything other than that, you really should use the interval notation. And I'll address that slightly more. Yeah, we got loads of time. I'll address that in a minute. So let's look at some examples that we're not going to graph define the range. We're just going to attack them algebraically to find the domain. So let's look first at x plus 2 over x squared minus 49. So I see a fraction. I see a rational function. But specifically, I see a denominator. And I know that if I have a denominator, I need to make sure that it's never going to be 0. So what we're going to start with is by setting the denominator equal to 0. And then we know we're going to exclude those values. So typically, when someone asks you what the domain of a function is, your job usually is to actually be like, well, what's not in the domain? Okay, I can find what's not in the domain, and then I want everything besides that. So you could either add 49 to both sides and take the square root. I would prefer to factor, because factoring is always, in my experience, factoring is almost always superior to doing something else. So if you have the option, I encourage you to factor. It's usually the best way to go. You're like, no, I don't want to do that. It's fine. You don't have to do that. Okay. So here we're going to get x equal to 7 and x equal to -7. And those are the values we want to exclude. We do not want to, we're not in the domain. So again, not required at all. I like to draw the number line just to help me figure out what I'm actually doing. So I'm going to draw a number line here. And on this number line, the only things I don't want are 7 and -7. When you're drawing a number line, you think about trying to have a domain or later on, you're talking about like the first derivative test and talking about, seeing where functions increasing, decreasing later on in your life. I want to strongly suggest that you only put numbers on the number line that you're looking at. Meaning, don't put 0 on there unless it's actually a critical point or something where you've got like this thing equal to 0. Right? You definitely don't want to add extra things in there because they're just kind of distracting. So these are the only numbers I don't want. I want everything else. So I like to scribble. I want all this. I want all this. I want all this. So my domain here is going to be everything from -infinity to -7, excluding -7, union -7 to 7, again, excluding both of those, but everything in between. So we can't just go -6 to 6, because there's a lot of numbers between -6 and -7. There's a lot of numbers between +6 and +7. And we're not just thinking integers here, we're thinking every possible real number. There's like literally an infinite number of numbers between 6 and 7. For real. And that's a lot, but there are. And then finally, we also want this last section over here, everything from 7 to infinity. Not including 7, not including -7, but literally getting every other number along the way. and this is the way you should write it. I'm not a huge, so not just me, most people, not a huge fan, although it's not technically incorrect, but I really would prefer not to see this all real numbers minus the set containing -7 and 7. That's just not my favorite. It's no one's favorite really, because it's also easy to kind of mess this up. So I would, again, encourage, request you to write your domains like this, where you're using the interval notation. But I will point out this is not a wrong way of doing it. It's just less favorable. Questions so far? Thank you for the questions so far. They've been good and helpful. Not typically. I'm trying to say no for sure, never. Well, that's not true. So the numerator can affect the domain. For example, if you took this next function and flipped it over instead, the numerator would totally affect the domain. So I would say yes if the numerator has a fraction or a logarithm or a square root or an even root. That's how the numerator can affect the domain. Maybe we'll do it. We got lots of time. Maybe we'll do an extra example at the end here. So let's look at this next one. Again, we're thinking domain. I see a fraction. I'll point out I don't see a rational function. The second function does not qualify as a rational function because the top and bottom are not both polynomials. We still, sometimes you'll definitely hear teachers say it looks rational-ish, or they'll even might say it's rational, even though it's not, because it's just kind of a word we use for fractions, but technically not a rational function. We're still going to deal with it the same sort of way we would, whereas we're going to look for all the usual things. So the first thing I see is I don't want the denominator to be 0. So denominator equal to 0, or I really want to exclude where the denominator is equal to 0. So I'm going to set the square root of x plus 8 equal to 0. I'm going to square both sides. And then I'm going to subtract 8. I don't know why I put parentheses there. I just did because I don't know. So I don't want x equal to -8. Great. Rhymes. Then we also have a square root. So we also have to say, well, the stuff inside the square root. So we also have the x plus 8 had better be greater than or equal to 0. Now, really, we probably could have combined this into one thing to said, well, we know x plus 8 needs to be greater than or equal to 0, but we also don't want it to equal 0. So we probably could have just gone straight to saying x plus 8 should be greater than 0. But it's also good to look at all the pieces separately. So here we want x greater than or equal to -8. Great. So we want x bigger than or equal to -8, but not equal to 8. So, sorry, -8. Apologies, I said 8. So we really just want, in the end, these things together mean x should be greater than -8. So is that -8 to infinity or -infinity to -8? If I'm bigger than -8, I want to be going to the right, towards infinity. Again, if you're not sure, you can always draw yourself a little number line. And then you have to be, okay, x is bigger than -8. That means I have numbers that are larger than -8 over here, but not -8 itself. So my domain here is everything from -8 to infinity, exclusive of both. One thing I will caution against, we always write the smaller or more negative numbers on the left and the bigger or more positive numbers on the right, or less negative numbers on the right. So it would be considered kind of incorrect to write this as infinity to -8, because we want to write the bigger numbers on the right and the smaller numbers on the left. Well, because whenever you have a square root, all the stuff inside the square root has to be greater than or equal to 0. You're right, at least I think you're right, in what you're saying is that we don't really want to include the 0, but I'm kind of looking at both parts separately. So you could always just be like, well, whatever's in the square root has to be greater than or equal to 0. And then also in this particular one, we know it shouldn't equal 0 because we're just that. So those are kind of two separate pieces. Right. So, but again, what I'm saying is I'm looking at these two things totally separately. So here I'm looking at the denominator and I'm like, okay, stuff in the denominator can't be 0, that means I can't get -8. Here, I'm totally not thinking about it being the denominator. I'm just thinking, oh, this is the stuff in a square root. And so if it's inside the square root, all I know is that it has to be greater than or equal to 0. Now you're right. We totally could have taken these two pieces together and been like, well, the stuff inside the square root can't be negative, and it also can't actually equal 0 because we're in the denominator, and that's a perfectly fine way to go at it as well. So here's a perfect example of the stuff inside the numerator being problematic, right? We have a square root of 2x plus 5 in the numerator, and we have an x squared plus 7x plus 10 in the denominator. So again, we have to look at these two pieces kind of separately. I like to start with the denominator personally. So the denominator, we're going to set and exclude where x squared plus 7x plus 10 is equal to 0. And hopefully it'll factor. It does. Okay, x plus 2 times x plus 5 equal to 0. So we're going to get x equal to -2, x equal to -5. And those are the values we want to exclude. One thing I've noticed over the years is that when you're taking where the denominator is equal to 0, you're kind of just pulling points out of the number line, right? You're just taking one out, taking one out. You're not taking out a whole swath of the number line. On the other hand, when you're dealing with a square root part or a logarithmic part, you're taking out whole intervals, whole chunks of the number line, because you're either getting like the right or the left or some piece in the middle, depending on how many factors you go. So we're going to remove those 2 points. And then we're also going to deal with the numerator. So we also have a square root. For the square root, we have to say the insides have to be non-negative. So we're going to set 2x plus 5 to be greater than or equal to 0. Totally fine to be equal to 0 here, right? Because it's in the numerator. All right, now we're solving for x. So we've got 2x greater than or equal to -5. And then x is greater than or equal to -5/2. You could arguably, okay, so that's the word I was looking for. You could factor out of 2 if you really wanted to, but when you're just solving for x, right? If you only got a single x, just solving for x is what you could do. All right, I'm a number line kind of guy. Number line is super useful, by the way. Like it comes up all the time when you're doing stuff in Calc 1. You're talking about finding functions, increasing, decreasing, stuff like that. Very useful. I encourage you to use it. So on my number line, I've got -5, -2, and -5/2, which is -2.5, should actually be between them. So it's like right here. -5/2. I don't want -5. I don't want -2. And I want everything that's bigger than or equal to -5/2. So I want everything to the right of -5/2. Except not -2, because we already said we didn't want it. So I want all this stuff here, including the -5/2. So not having -5 is kind of pointless, I guess, or I guess it didn't really matter because we really don't want anything over there. -5 is already too negative for that square root to even deal with. So here our domain is everything starting at -5/2 is the lowest we go. This is also another reason I like to write the number line, because if you look at this, you can be like, oh, I need to go from left to right. So if I start at the leftmost point, I've got -5/2. Brackets, because we want to include it. Comma, go up to the next kind of place where we have an issue is -2. So I have to stop at -2, say I don't want -2, so we're excluding it. But then I want everything just on the other side of -2. So I start back up at -2, still being excluded. And then all the way to infinity because there's nothing else to stop us. That's everything from -2.5 up to infinity, except for the 1 point at -2 that we don't want. So, talking about domain, it's really just the question of what do we want, what do we don't want. You can also, if you're not sure after you found domain, you can kind of check and be like, well, does the stuff in the places I picked actually work? Like if you pick a number bigger than -2, like 0, can you actually plug it into the function and get a real result? Well, yeah, if we plug in 0 here, 2 times 0 plus 5 is 5, and the square root of 5 is a real number, 2 point something. If you plug in 0 on the bottom, you don't get 0, so we're good. On the other hand, if you pick something way to the left, like, I don't know, -3, 2 times -3 is -6, and -6 plus 5 is -1, and we can't take the square root of -1 and get a real number out. So that's why -3 and all the things to the left of -5/2 are not in the domain because they make the inside of the square root negative, and that's a problem. Okay. Last one on this page, the natural log of some stuff. Really, when I'm seeing, and this is words I use all the time, stuff. I use stuff all the time. I've got the square root of some stuff over some stuff. So I said the square root of my stuff, the stuff had to be greater than or equal to 0. Or dividing by some stuff, that stuff, I'm going to exclude where it's equal to 0. Here I got the natural log of some stuff. And what I'm going to start off by saying is, oh, that stuff had better be strictly greater than 0. So x to the 4th plus 9x cubed plus 14x squared had better be strictly greater than, not equal to 0. Now, whenever you're solving something greater than 0, if you've or greater than or equal to 0, either way, if you've just got a single x to the first, just solve for x. It's a linear equation, it's not too bad. If you've got higher powers of x, we have to use factoring. You can't just try to solve for x here. So we're going to factor out our greatest common factor first, which is an x squared. And then we're left with an x squared plus a 9x plus 14. Then we're looking for numbers that multiply to 14 and add to 9. I think 2 and 7 fit the bill. So I got x plus 2 and x plus 7. So the numbers we need to think about are x being 0, -2, and -7. But those are not the numbers we're excluding necessarily, although we are going to exclude them because each of those would make that expression equal to 0. We don't just want to exclude where it's equal to 0, we also want to exclude all the values that make it negative. Or we only want where this thing is positive. This is definitely where you need to use a number line. On a number line, I put my points. And honestly, I kind of think about this as like if I was graphing this polynomial, where would it be positive? Now I know my original function is not a polynomial. I'm just thinking about the inside being a polynomial. But if I were to graph that, where would it be positive, where would it be negative? You could actually graph it. I don't want to actually graph it. I really just want to pick points in each of these 1, 2, 3, 4 intervals and figure out if the whole thing's positive or negative. So I'm going to pick something larger than 0, like 1, and plug it in. See that 1 squared is positive, 1 plus 2 is positive, 1 plus 7 is positive, and the positive is positive is positive is positive. And it wouldn't matter if I picked 1 or 1,000, right? 1,000 would, right? All of these things are still positive. Because I'm picking something that's larger than 0, all these things are positive. If I pick something less than 0, like, well, I should say not just less, between 0 and -2. I pick -1. You can pick something else. You can pick -1.5. I'm going to pick negative. -1 plus 7 is positive. -1 plus 2 is positive. But -1 itself is negative, but if you square it, it's still positive. So still positive times positive times positive. The whole thing is still positive. All right, so now we go to the other side of -2, pick something like -3. -3 plus 7 is positive. -3 plus 2 is negative. -3 is negative, but squaring it still becomes positive. Now I have a positive times a negative times a positive, so the whole thing is negative. I would point out that the 0 here came from this term with an even multiplicity and went from one side to the other. The sign stayed the same. This -2 came from a factor with an odd multiplicity and went from one side to the other. The sign changed, or you crossed. Here you bounced, there you crossed. So -7, if we were thinking graphically, coming from this factor with an odd multiplicity, are we bouncing or crossing? We're crossing. If we cross, you go from negative to positive. Or you can plug in points. But this bouncing crossing idea always works with this even odd power kind of thing. So you can say, oh, factors that came from even powers, you're going to have the sign staying the same. Factors that come from odd powers are going to have signs that change. Kind of nice. It works. So what are we trying to do? Find the domain. Try to see where this thing is greater than 0. So that means we want where it's right. We want the positive parts. We do not want the negative parts. And since we want it to be greater than and not equal to 0, we also want to exclude all of these points where it's equal to 0. So I want everything from all the way to negative infinity up to -7, exclusive of -7, union I don't want anything from between -7 and -2. That's out. I want everything from -2 to 0, exclusive of both. Union, I want everything from 0 onward. And that would be the domain of this particular function. So, domain, 3 things to look for. Are we dividing by 0? We don't want to do that. Am I taking a square root of a negative? I don't want to do that. Am I taking a logarithm of a negative or a 0? I don't want to do that. So those are the things we try to make sure we are not doing. What's this last one here? Oh yeah, this last one. Okay, good. I'm like, why is this question? I remember there's a homework question like this. So, domain and range of this function. So, just like any other time, if I'm finding domain, I take my original expression. Emphasize that I'm gonna take my original expression and see what problems I have. Well, I can't have the denominator being 0, so we're going to exclude where x minus 8 is equal to 0. So that's going to be x equal to 8. So I don't want x equal to 8. So my domain is everything but 8. Which hopefully is not terribly surprising. Any other value is fine. I should mention it's totally fine for the denominator here to be negative. I've definitely seen people in the past be like, oh, I want everything where x is like bigger than 8. We don't want that here. Denominators can be positive or negative. The only times negatives are problems is if they're showing it in square roots or fourth roots or logarithms or 6 roots or any. But now the range for this one. The range. So again, we haven't talked about finding the range using inverses yet. We're going to next class on Wednesday. Last class of this week, by the way. No class on Friday, just a reminder. So we're going to graph this. And typically when we graph rational functions, we usually like to take the step of simplifying if we can, meaning factoring and canceling if that happens to happen. It doesn't usually happen. It does happen here. So if we factor the top, it's equal to x minus 8 times x plus 3 over x minus 8. So I graph this thing, well, I can cancel the x minus 8s. It's equal to x plus 3, except what number is not in the domain of this function? My favorite number, 8. So this function is equal to x plus 3, except x is not allowed to equal 8. Okay, it's totally fine. It means we're going to have what kind of thing at 8? A whole. So when I graph this, I know how to graph the line y equals x plus 3. It's a straight line going up from left to right. It's got a y-intercept of 3. And it's going to look like this, except when I get to 8, there's going to be a hole. And the question is, what's the y value of that hole? Well, if this function is f of x equal to x plus 3, except x is not allowed to equal 8, if x were allowed to equal 8, what would you get? I think I heard the right number. You get 11, 8 plus 3. You just plug in the 8 to the function that you're not allowed to plug it into. So that's what we have there. We have a hole at 8, 11. Another way to think about this is you can pick, and this is actually kind of an important area. You can pick numbers really close to 8 for x, like 7.9. In fact, let's do it. Make a table. X, y. It's equal to x plus 3, except x can't equal 8. So if x was like 7.9, y would be 7.9 plus 3 is 10.9. Or if x was 7.99, y would be 10.99. Or if x was 7.99. Right? It looks fairly clear, I think, that the closer and closer and closer x gets to 8, the closer and closer and closer y gets to 11. So this point here, this one single point we're missing is 8, 11. We get these other points that are super close to it though. So that's why we're only missing that one singular point, because everything around it is totally filled in just fine. What does that mean as far as answering the question? Well, the question was to find the domain, which we already did. right here. Just label it. And also the range. Well, looking at this graphically, this function goes as low as you want. This function goes as high as you want. The only y value that's missing is 11. So our range here, everything but 11. Negative, whoops, come on, you can draw an infinity. Negative infinity up to 11. That's not, wow, can I draw an 11? Okay. Union 11 to infinity. That's your range. So often if you have a hole in the graph, that one y value will get excluded from the range. Not always though. You can have weird graphs is what we should really kind of come down to at the end here, is that sometimes graphs are just weird. Sure. I didn't leave myself enough room to write that on there. Terrible. How much time we got? How we got there? We can just call it a day. We need to cram in another example with 2 minutes left. So again, the big picture here is if you're finding domain, you're just looking for making sure the denominator can't be 0. You're not taking a square root of a negative number. You're not taking a logarithm of a 0 or a negative. That's it. Wednesday, we'll talk about how to find range using the inverse functions, which is really just finding domain again. How exciting. These pens might be done. What's that? Just so you can take a look. Basically, we were just saying what kind of how to do what we do. So basically, I mean, it's kind of what we talked about in class, right? If you can't have division by 0, so the way we deal with that is by setting equals 0, excluding the values. Can't take the square root of negative. Can't take logarithm of 0 or negative. You're welcome to take a look at that for a minute. You're fine.
I noticed that I lost some points on attendance. I think I just forgot to fill out one of the forms.
So it's totally, so the attendance counts for 0% of your grade. So don't sweat. Like if you miss the attendance, don't worry about it. It's not a huge deal.
All right.
It's more just for our purposes, keeping track of students and serve. But yeah, if the attendance will not affect your grade in any way, shape, or form.
All right. Thank you.
You're welcome. I'm trying to do the thing. There we go. See y'all later.